Welcome. If I could have the first slide, please. Contrary to calculations made by some engineers, bees can fly, dolphins can swim, and geckos can even climb up the smoothest surfaces. Now, what I want to do in the short time I have is to try to allow each of you to experience sort of the thrill of revealing nature's design. I get to do this all the time, and it's just incredible. And I want to try to share just a little bit of that with you in this presentation. The challenge of looking at nature's designs, and I'll tell you the way that we perceive it and the way we've used it. The challenge, of course, is to answer this question. What permits this extraordinary performance of animals that allow them basically to go anywhere? And if we can figure that out, how can we implement those designs? Well, many biologists will tell engineers and others organisms have millions of years to get it right. They're spectacular. They could do everything wonderfully well. So the answer is biomimicry. Just copy nature directly. We know from working on animals that the truth is that's exactly what you don't want to do. Because evolution works on the just good enough principle, not on a perfecting principle. And the constraints in building any organism, when you look at it, are really severe. Natural technologies have incredible constraints. Think about it. If you were an engineer and I told you that you had to build an automobile, but it had to start off to be this big, it had to grow to be full size, and it had to work every step along the way. Or think about the fact that if you build an automobile, I'll tell you that you also, inside it, have to put a factory that allows you to make another automobile. And you can absolutely never, because of history and the inherited plan, start with a clean slate. So organisms have this important history. Really, evolution works more like a tinkerer than an engineer. And this is really important when you begin to look at animals. Instead, we believe you need to be inspired by biology. You need to discover the general principles of nature and then use these analogies when they're advantageous. This is a real challenge to do this because animals, when you start to really look inside them, how they work, appear hopelessly complex. There's no detailed history of their design plans. You can't go look it up anywhere. They have way too many motions for their joints, too many muscles. Even the simplest animal we think of is something like an insect, and they have more neurons and connections than you can imagine. Now, how can you make sense of this? Well, we believed and we hypothesized that one way animals could work simply is if their control of their movements tended to be built into their bodies themselves. What we discovered was that 2, 4, 6, and 8-legged animals all produce the same forces on the ground when they move. They all work like this kangaroo. They bounce. And they can be modeled by a spring mass system, although we call this a spring mass system because we're biomechanists. It's actually a pogo stick. They all produce the pattern of a pogo stick. How is that true? Well, a human, one of your legs, works like 2 legs of a trotting dog, or works like 3 legs together as one of a trotting insect, or 4 legs as one as a trotting crab. And then they alternate in their propulsion. But the patterns are all the same. Almost every organism we've looked at this way, you'll see next week, I'll give you a hint, there'll be an article coming out that says that really big things, like T-Rex, probably couldn't do this, but you'll see that next week. Now, what's interesting is the animals, then we said, bounce along in the vertical plane this way, and in our collaborations with Pixar and A Bug's Life, we discussed the bipedal nature of the characters, of the ants, and we told them, of course, they move in the other plane as well, and they asked us this question. They say, why model just in the sagittal plane or the vertical plane when you're telling us these animals are moving in the horizontal plane? This was a good question. Nobody in biology ever modeled it this way. We took their advice, and we modeled the animals moving in the horizontal plane as well. We took their 3 legs, we collapsed them down as one. We got some of the best mathematicians in the world from Princeton to work on this problem. And we were able to create a model where animals not are only bouncing up and down, but they're also bouncing side to side at the same time. And many organisms fit this kind of pattern. Now, why is this important to have this model? Because it's very interesting. When you take this model and you perturb it, you give it a push, as it bumps into something, it self-stabilizes with no brain or no reflexes, just by the structure alone. It's a beautiful model. Let's look at the mathematics. That's enough. The animals, when you look at them running, appear to be self-stabilizing like this, using basically springy legs. That is, the legs could do computations on their own. The control algorithms, in a sense, are embedded in the form of the animal itself. Why haven't we been more inspired by nature in these kinds of discoveries? Well, I would argue that human technologies are really different from natural technologies. At least they have been so far. Think about the typical kind of robot that you see. Human technologies have tended to be large, flat with right angles, stiff, made of metal. They have rolling devices and axles. There are very few motors, very few sensors. Whereas nature tends to be small and curved, and it bends and twists and has legs instead and appendages, and it has many muscles and many, many sensors. It's a very different design. However, what's changing, what's really exciting, and I'll show you some of that next, is that as human technology takes on more of the characteristics of nature, then nature really can become a much more useful teacher. Here's one example that's really exciting. This is a collaboration we have with Stanford, and they developed this new technique called shape deposition manufacturing. It's a technique where they can mix materials together and mold any shape that they'd like and put in the material properties. They can embed sensors and actuators right in the form itself. For example, here's a leg. The clear part is stiff, the white part is compliant, and you don't need any axles there or anything. It just bends by itself beautifully. So you can put those properties in. It inspired them to show off this design by producing a little robot they named Sprawl. Our work has also inspired another robot, a biologically inspired bouncing robot from the University of Michigan in McGill, named Rex for robot hexapod. And this one's autonomous. Let's go to the video and let me show you some of these animals moving and then some of the simple robots that have been inspired by our discoveries. Here's what some of you did this morning, although you did it outside, not on a treadmill. Here's what we do. This is a death-head cockroach. This is the American cockroach you think you don't have in your kitchen. This is an 8-legged scorpion, 6-legged ant, 44-legged centipede. Now, I said all these animals are sort of working like pogo sticks. They're bouncing along as they move. And you can see that in this ghost crab from the beaches of Panama and North Carolina. It goes up to 4 meters per second when it runs. It actually leaps into the air and has aerial phases when it does it, like a horse. And you'll see it's bouncing here. What we discovered is whether you look at the leg of a human like Richard, or a cockroach, or a crab, or a kangaroo, the relative leg stiffness of that spring is the same for everything we've seen so far. Now, what good are springy legs then? What can they do? Well, we wanted to see if they allowed the animals to have greater stability and maneuverability. So we built a terrain that had obstacles 3 times the hip height of the animal that we looked at. And we were certain they couldn't do this. And here's what they did. That animal ran over it, and it didn't even slow down. It didn't decrease its preferred speed at all. We couldn't believe that it could do this. It said to us that if you could build a robot with very simple springy legs, you could make it as maneuverable as any that's ever been built. Here's the first example of that. This is the Stanford shape deposition manufactured robot named Sprawl. It has 6 legs. They're the tuned springy legs. It moves in a gait that an insect uses, and here it is going on the treadmill. Now, what's important about this robot compared to other robots is that it can't see anything, it can't feel anything, it doesn't have a brain, yet it can maneuver over these obstacles without any difficulty whatsoever. It's this technique of building the properties into the form. This is a graduate student. This is what he's doing to his thesis project. Very robust if a graduate student does that to his thesis project. This is from McGill and University of Michigan. This is the Rex making its first outing in a demo. Same principle.
Wow.
It only has 6 moving parts, 6 motors, but it has springy, tuned legs. It moves in the gait of the insect. It has the middle leg moving in synchrony with the front and the hind leg on the other side, sort of an alternating tripod, and it can negotiate obstacles, just like the animal.
Oh my God.
You go on different surfaces. Here's sand, although we haven't perfected the feet yet, but I'll talk about that later. Here's Rex entering the woods. Again, this robot can't see anything. It can't feel anything. It has no brain. It's just working with a tuned mechanical system with very simple parts, but inspired from the fundamental dynamics of the animal.
Oh. I love him, Bob.
Here's going down a pathway. I presented this to the Jet Propulsion Lab at NASA, and they said that they had no ability to go down craters to look for ice and life ultimately on Mars. And they said especially with legged robots because they're way too complicated. Nothing can do that. And then I talked next. And I showed them this video with a simple design of Rex here. And just to convince them we should go to Mars in 2011, I tinted the video orange just to give them the sense of being on Mars.
Oh.
Another reason why animals have extraordinary performance and can go anywhere is because they have an effective interaction with the environment. The animal I'm going to show you that we studied to look at this is the gecko. We have one here. And notice its position. It's holding on. Now, I'm going to challenge you. I'm going to show you a video. One of the animals is going to be running on the level, and the other one's going to be running up a wall. Which one's which? They're going at 1 meter a second. How many think the one on the left is running up the wall? Okay. The point is, it's really hard to tell, isn't it? It's incredible. We looked at students do this, and they couldn't tell. They can run up a wall at 1 meter a second, 15 steps per second, and they look like they're running on the level. How do they do this? It's just phenomenal. Oh, the one on the right was going up the hill. How do they do this? They have bizarre toes. They have toes that uncurl like party favors when you blow them out, and then peel off the surface like tape. Like if you had a piece of tape and we peel it this way. They do this with their toes. It's bizarre. This peeling inspired iRobot that we work with to build mecho geckos. Here's a legged version and a tractor version, or a bulldozer version. Let's see some of the geckos move with some video, and then I'll show you a little bit of clip of the robots. Here's the gecko running up a vertical surface. There it goes in real time. There it goes again. Obviously, we have to slow this down a little bit. You can't use regular cameras, so you have to take 1,000 pictures per second to see this. And here's some video at 1,000 frames per second. And I want you to look at the animal's back. Do you see how much it's bending like that? We can't figure that out. That's an unsolved mystery. We don't know how it works. If you have a son or a daughter that wants to come to Berkeley, come to my lab and we'll figure this out. Okay? Send them to Berkeley, because that's the next thing we want to do. Here's the gecko mill. It's a see-through treadmill with a see-through treadmill belt, so we can watch the animal's feet and videotape them through the treadmill belt to see how they move. And here's the animal that we have here running on a vertical surface. Pick a foot and try to watch a toe and see if you can see what the animal's doing. See it uncurl and then peel these toes. It can do this in 14 milliseconds. This is unbelievable. All right, here are the robots that they inspired, the Mecho geckos from iRobot. First, you'll see the animal's toes peeling. Look at that. And here's the peeling action of the Mecho gecko. It uses a pressure-sensitive adhesive to do it. Peeling in the animal, peeling in the Mecho gecko. That allowed it to climb autonomously. It can go on the flat surface, transition to a wall, and then go onto a ceiling. There's the bulldozer version. Now, it doesn't use pressure-sensitive glue. The animal does not use that. Okay, but that's what we're limited to at the moment. What does the animal do? The animal has weird toes, and if you look at the toes, they have these little leaves there. And if you blow them up and zoom in, you'll see that there's little striations in these leaves. And if you zoom in 270 times, you'll see it looks like a rug. And if you blow that up and zoom in 900 times, you see there are hairs there, tiny hairs. And if you look carefully, those tiny hairs have striations. And if you zoom in on those 30,000 times, you see each hair has split ends. And if you blow those up, they have these little structures on the end. The smallest branches of the hairs look like spatula, and an animal like that has 1 billion of these nano-sized split ends to get very close to the surface. In fact, there's the diameter of your hair. A gecko has 2 million of these, and each hair has 100 to 1,000 split ends. Well, think of the contact of that that's possible. We were fortunate to work with another group at Stanford that built us a special MEMS sensor that we were able to measure the force of an individual hair. Here's an individual hair with a little split ends there. When we measured the forces, they were enormous. They were so large that a patch of hairs about this size, the gecko's foot, could support the weight of a small child, about 40 pounds easily. Now, how do they do it? We've recently discovered this. Do they do it by friction? No. Force is too low. Do it by electrostatics? No, you can change the charge, they still hold on. Do they do it by interlocking? That's kind of like a Velcro-like thing. Nope, you can put them on molecularly smooth surfaces, they don't do it. How about suction? Yeah, they stick on in a vacuum. How about wet adhesion or capillary adhesion? They don't have any glue, and they even stick underwater just fine. If you put their foot underwater, they grab on. How do they do it then? Believe it or not, they grab on by intermolecular forces. By van der Waals forces. You know, you probably had this a long time ago in chemistry where you have these two atoms get close together and electrons move around. That tiny force is sufficient to allow them to do that because it's added up so many times with these small structures. What we're doing is we're taking that inspiration of the hairs, and with another colleague at Berkeley, we're manufacturing them. And just recently, we've made a breakthrough where we now believe we're going to be able to create the first synthetic, self-cleaning, dry adhesive. Many companies are interested in this. We also presented to Nike even. We'll see where this goes. We were so excited about this that we realized that that small size scale and where everything gets sticky and gravity doesn't matter anymore, we needed to look at ants and their feet because one of my other colleagues at Berkeley has built a 6mm silicone robot with legs, but it gets stuck, doesn't move very well. Well, the ants do, and we'll figure out why, so that ultimately we'll make this move. And imagine you're going to be able to have swarms of these 6mm robots available to run around. Where is this going? I think you can see it already. Clearly, the internet is already having eyes and ears. You have webcams and so forth. But it's going to also have legs and hands. You're going to be able to do programmable work through these kinds of robots so that you can run, fly, and swim anywhere. We saw David Kelly's beginning of that with his fish. So in conclusion, I think the message is clear. If you need a message, if nature's not enough, if you care about search and rescue or mine clearance or medicine or the various things we're working on, we must preserve nature's designs. Otherwise, these secrets will be lost forever. Thank you.